Hello, discrete math fans. We're going to make a definition to say that two digital logic circuits are equivalent if and only if their input-output tables are identical. So you can have two circuits that look wildly different, but when you look at their input-output tables, they actually show the same thing. So the way that we're going to show that two digital logic circuits are equivalent is by writing down the Boolean expressions corresponding to the circuits and then showing that they are logically equivalent, at least when we regard them as statement forms. All right, so here's an example. There's two different circuits here. There's this circuit up here, which is more complicated, and then we've got a circuit down here. We'd like to show that these are equivalent. Now, they're not the same circuit, but they're equivalent in that whatever we put in for P and Q, we're going to get the same output. Now, the way that we're going to show this is actually using the various properties that are on page 35 in your book. This is theorem 2.1.1. Among these are things like Demorgan's law and the distributive law. We have a lot of different laws that allow us to make equivalencies between statement forms. And just to remind you, here's the list of equivalencies that we showed earlier. So we have commutative law, associative law, identity law, law of the excluded middle, double negative law, idempotent laws, universal bound laws, Demorgan's laws. These are the important ones. There's the absorption laws, and then the negations of the tautology and contradiction. All right, so our solution is going to be that the first circuit has this Boolean expression, the negation of not P and Q and not P, and then a Boolean expression for the second circuit is not P or Q. Now we could simply create a truth table for these expressions and then show that they're logically equivalent that way, but let's try to use the named equivalencies that we showed. All right, so we'll start with the more complicated looking expression, which is not parentheses, not P and Q, close parentheses, and not P. Our first step is to use Demorgan's law on the first portion of it here. So if we use Demorgan's law, then this piece turns into this, the and turns into an or. Technically, we're also using a double negative in there. Now we'll use the distributive law. So we're going to take this not P and distribute it to the P and the not Q. And so these are the ands on the inside that we get out of this and. Now we'll use the negation law. So P and not P turns into a contradiction. But if you have a contradiction and you OR that with some statement, then the contradiction doesn't matter anymore. We just drop it. That's the identity law. And in the final step, we'll use Demorgan's law to go from not Q and not P to not, and then in parentheses, P or Q, which is the final expression that we came up with. Okay, that's all for now.